So, this is something that on the surface looks like it's totally different from what we've been talking about. First of all, I'm seeing discrete random variable. Well, we kind of know what discrete means, just from stuff we've talked about before. Random variable, we haven't looked at. And you go, okay, this is just changing everything. And if you read this definition in the book, numerical measure of the outcome of a okay. What does that even mean? Well, here's an example. If I flip a coin 3 times, or if I flip 3 coins all at once, here's the possibilities that could come up. All heads, 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 tails. And so I just made a list of what's in that set of outcomes. And that's all of them. There's 8 of them. So I could say, all right, let's let random variable x, and you're going to see x used a lot for random variables, and sometimes capital Y and sometimes capital Z, but x is the big one. Let's let capital X stand for the number of heads. Okay, so does X fit the definition? Is it the outcome of a probability experiment? Yeah. Its value is determined by chance? Yeah. So look what I'm doing here. I'm just saying, all right, I'm going to get a certain number of heads. What values could X have? From what to what? 0. I might not get any heads at all. Could I have just 1 head? Yeah. 2? 3? 4? All right, so this is the set of outcomes I've got. We're just calling that X. X is the number of heads. I could have said let X be the number of tails. But we're just letting it equal the number of heads. X is a random variable, meaning it's just standing for the number of things that I'm looking for. That's all it means. All right, then we get to the discrete part. And don't write anything for a second. Just look at this. What's a discrete random variable? It's either finite, like our flipping the 3 coins thing, or you can count the values. Okay. I can put it on a number line with space between. And so if you look down here, there's a little example of a discrete random variable. Notice whatever that variable is, it looks like it's going 0, 1, 2, 3, 4, at least what we can see. Contrast that with a continuous random variable. Notice over here, there's no individual points. It's a continuous kind of thing. Excuse me. Hence the name continuous random variable. It could be, if you went further in statistics, you would get into random variables that might have different shapes. Continuous, like an f of x kind of thing. All right, stop right there. Well, guess which kind we're going to look at? Right, discrete. To really do continuous random variables, you need to know calculus. And since that's not part of this class, that's going to get left out. Now, like I said, if you went further in statistics in college, say you decide you want to major in that or something, then you'd get into those calculus-based things. Just like if you really wanted to get into physics, you'd get into a calculus-based physics class in college. Let's keep going. I want to know, here's just different random variables. I want to know if these are continuous or discrete. So look at 5a. What do you think? Discrete, I'll go with that. The time it takes to fly from New York City to Los Angeles. The number of hits to a website in one day. The amount of snow in Toronto. The time it takes for a light bulb to burn out. The weight of a T-bone steak. The number of free throw attempts before the first shot is made. Yep. And in a random sample of 20 people, the number with type A blood. Now think about that last one. If we said X is that random variable, what values could it take on? Could it be 0? And could it go all the way up to all 20 of them having type A blood? Yeah. So 0 through 20 would be the values that that random variable could take on. All right, so I took our little let X be the number of heads kind of thing. And now then, we're going to talk about a probability distribution of a discrete random variable. Okay, that's a lot of words. We've looked at probability distributions before. What do we have to have? We have to have the value we're looking at and its probability. So we're going to do the same thing here. X could be 0, 1, 2, or 3. I got to find the probability of each of those. So what's the probability of getting 0 heads? 1 out of 8, thank you. And if you want to change that to a decimal, what would it be? 1 out of 8's fine, 1/8, but I think as a decimal, which is what the book's going to use most of the time, it's just 0.125. Okay? How many of those things just have 1 head? Three of them? Okay, so if I change that to a decimal, 0.375. It's just 3 times that 1/8 thing. How about 2 heads? So another 0.375. Let's see if I can do it right. 375. And then 3 heads. Thank you. There is a probability distribution for this random variable X that we're talking about. Anything drastically new? Not really. It's just the idea that I can let a variable stand for the number of things that might happen. As long as what? The outcome is determined randomly. All right. Couple of rules. Just look at them. Y'all already know them. Look what the first one says. If I add up all the probabilities for that random variable, I'm going to get 1. Where have we seen that before? When we first started talking about probabilities, that was, what, rule 2? All the probabilities in the sample space add up to 1. Well, is this thing right here a sample space? Yeah. That's all the ways those 3 coins could come up. So rule number 1 here, we've already seen. And then look at 2. All the probabilities have to be between 0 and 1. Y'all already know this. Look at this distribution here. Do those all add up to be 1? What do you think without even doing it? Yeah. If I add 0.125 and 0.375, guess what I get? 0.5. And there's 2 of those in there, so that all adds up to 1. So this thing right here meets both of those rules. All right. Let's take a look at some questions here. Number 1, is that a probability distribution or not? Yep, all of them are all these probabilities are between 0 and 1. Do they all add up to 1? Done deal. That's all you got to ask. The reason I bring this up is I looked at the homework for this, and about half the questions are that. Is this a probability distribution or not? I don't think the homework's going to take you a long time. Look at number 2. All of these add up to 1. Or all of them between 0 and 1? Yeah. Look at number 3. No. One minor little detail. For 50, it's a negative number. If I added all those up, might I get 1? If I did, though, it still fails because of that negative value. That's about half the questions on the homework.
I think we just didn't have a class in that then.
You could work for the government with an attitude like that. All right, here we go. Now, how do I get the average? How do I get the... Now, if we're letting X stand for a random variable for the number of heads, let's go back and look at something here. Do I just add up 0, 1, 2, 3 and divide by 4? How do I get your grades in here? Do I just add up all those homework grades and all the quiz grades and the midterm and final, just put them in one big box and just say I'm just going to average those? No. What do I do? I do. The weight of them comes into play. So I average the tests together, I average the quizzes together, I average the homework together, and those all have different weights. Well, that's all this is saying. The random variable X having a value of 1 or 2, that should count more because there's more of them, right? So look how we get the mean. It says, and notice the way they're writing it, mu of X. Wait a minute, anytime we see mu, that means the whole population, right? That's what we've used it for. Does this represent all the ways that flipping 3 coins could come up? Yeah. So that is a population we're looking at. That's going to get important when we look at the calculator here in just a second. Look what it says to do. You multiply the value times its probability. I'll say that again. You multiply the value times its probability and add them all up. Now, this isn't like an average you've seen before, but this is how I get your grades. Okay. So mu of X here, the X we've been using, is going to be what? 0 times, what's its probability? 0.125. Yeah? The likelihood of getting 0 heads is 1 out of 8. Plus the 1 times, what's its probability? Right? Plus 2 times, same thing, plus 3 times that. Why don't y'all solve those on your calculator and let's see what we get. So think about this. We're saying that. The mean of those values, the mean of random variable x, is 1.5. What does that, no pun intended, what does that mean? It means if I did this over and over and over again, thousands of times, and then divided how many heads I got by how many times I did it, the average would come out to be 1.5. Here's the definition for you. This is also known as the expected value. Has a lot of real world implications. So if I say the mean of this random variable, or I say the expected value of this random variable, they both mean the same thing. Notice that mean is not any of the values we could get. How many times am I going to roll 1.5 heads? Never. This is an average. It doesn't have to come out to be one of the values. Just like if I averaged all your homework grades together, the average might not be one of the values you got on the homeworks. Stop right there. Are we good? We don't want to do all the math work by hand, and there's a couple of ways we can use the calculator to make this work easier. First thing we can do is to use it to simulate what we'd really be doing by hand. So we'll put all of x's values into L1. And the corresponding probabilities into L2. Then we'll go all the way up to the top of L3 and tell that list to multiply the contents of L1 by the probabilities in L2. And then we're going to exit this list view by pressing second and mode, which is quit. Now we're going to go to the actual list part of the calculator by pressing second stat, and that takes us to the list area. We're going to come all the way out to the math part of that and come down to choice number 5, which is the sum function. In other words, we're going to tell the function we want to get the total of the values in L3. This value that the function gives us is the mean, or the average, of that random variable x from our coin flipping example. So to recap what we did on the calculator, we multiplied each value in the distribution times its probability. Then we added all of those products up, and that's exactly what we do by hand to find the weighted mean. We're just following the formula. If I can get the average, I can get the standard deviation. This is in the book. Just look what it's saying to do. It's saying, first of all, on the inside of that radical, it says, take the mean, subtract that mean from each value, okay, square that difference, and multiply that times the probability. Huh? And then take square root of it. So let's use our flipping coin kind of thing again. And so I would have what? I would have 0 minus what? 1.5. That's our mean. Squared. Times what's the probability of 0? That. You good? I'm taking 0, the first value that the number of heads could be, subtracting the mean, which is right here, Multiply it times the probability. Plus 1 minus 1.5 squared times this. Seem kind of drawn out to you? Plus 2, got to subtract 2 minus 1.5 squared times the probability of 2, which is plus 3 squared. Let me scoot all this over. Times the probability. That's how you actually do it. That formula is in your formula pages. So if I ask you to show your work, which you know the quiz is going to do, this is what you'd write down. Now, are you really going to go through all that on a calculator? No. Even though the formula for finding the standard deviation of a random variable looks kind of complicated, actually doing the work on the calculator is really easy. Take a look. We've already got our values that the random variable could take on in L1. We've got the probabilities of each one of those values in L2. Now we don't need L3 for this, so we can just forget about it. Once we've got those values in L1 and L2, like we do here, then let's get out of this section by hitting second mode. And then we're going to come back in by hitting stat, but this time we're going to go to the calc area. First choice there is 1var stats. And we've seen that before. And you might be going, well, wait a minute. No, we've got two variables. We've got the stuff in L1 and the stuff in L2. But remember, L1 contains the values, the actual values of our random variable. L2 just contains a probability. So we still just have one variable. Anyway, we're going to choose 1var stats, and we're going to make sure that we have L1 chosen for the list of values, and then we're going to make sure that we've got L2, which contains the probabilities. That's going to be called the frequency list here. In other words, those are the weights that we're going to give to the values in L1. We come down and hit calculate, and here's what we get. Look down on line 5. That says the standard deviation for the population, which is what all of those values in the random variable x are, population of values. It says the standard deviation for that is 0.8660 rounded off to 4 decimal places. That's the actual standard deviation. That's what you would get if you plugged all those values into that formula and processed doing it by hand. Here the calculator just gives it to us that fast. And notice something else. At the very top it says x bar is 1.5. Well, that's the mean of this random variable x. So here's a real fast way of getting both the mean and the standard deviation of random variables. So all you'd have to do is just write the formula down with your values plugged in and then let the calculator do the real work. So what's an insurance company do? It sells you a policy and they're betting you're going to live. They charge you money for the policy and they say, you know, if you die, we lose. Of course, you did too because you died. But so they sell you a policy. Well, how do they know how much to charge for that policy? They know, I promise you, insurance companies know about how many 20-year-old males are going to die in Texas this year. They know. Why? Because they keep track of that sort of thing. That's their business. And they've got some really good statisticians that go, Okay, let's figure this up. What are we letting X stand for here? It says compute and interpret the expected value. Wait a minute, that's just the mean, isn't it? So compute and interpret the expected value of this policy to the insurance company. Okay, so if I let X be the cost to the company, here's X, here's the probability of X. Okay, X only has two values, right? If you live, what's it cost the company? Let me say again, if you live, what does it cost the company? Right. So nothing. Now, what's the probability of that? Well, it tells us up here the probability of a 20-year-old male living for a year is that. So that's going to be 998,734. Yeah? If this guy dies, what's it cost the company? They don't want to pay out $250,000. But this is sort of like playing slot machine in Vegas or someplace. They're going to win more than they lose, right? Look at the probability of this guy living. It's pretty close to 1. Okay, what is that probability? In your calculators, if you would say 1 minus this 0.998, blah, 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 what do we get? 1 what? Thank you. How do we get the mean? We multiply these two things together, and add them up. So I've got 0. Oh. So the mean of X equals 0 times 0.998734 plus negative 250,000 times what? 0.001268. 0.001268. 66. Then I'm going to quit saying 8. Okay, thank y'all. All right, so I don't have to multiply these two together because I know I'm going to get 0. So what's negative 250,000 times 0.001266? Negative 317? 16? Thank you. What does that mean? What does that represent? That's the average that's going to cost the company. Over what? One person? No, over thousands. This represents what? The average cost to the company if they sell thousands of these policies. On average, if they sell this policy to 10,000 20-year-olds, on average, it's going to cost them that, $316.50. What are they charging? Oh. $350, just plain old $350. Let's subtract that. Now what? If I did my math right, What does that mean? They're going to make a profit of $33.50 per policy. So if they sell 100,000 of those, that's a lot of profit, and that's what they do. They don't just sell 10 policies. It wouldn't be worth it to them. They would lose money and go out of business. Does that mean they're ever going to pay out, or they're ever going to make $33.50? No. It means they're either going to pay out nothing or they're going to pay out $250,000. But if you spread that out over the long run, this expected value and the average are the same thing. That company expects to make over $33 per policy. Isn't that what slot machines do? Yeah. They are set with certain probabilities. The state of Nevada, or wherever those things are, sets limits on how low they can make those probabilities. Because they set the machines. So they're expecting to make a profit, and they will. Does that make sense? Just think about that for a second. Please don't write this down. This is problem number 30 from the end of the section. So let's just go through it together. So you've got an investment counselor. He says if the economy remains strong, his investment will result in a profit of $50,000. If the economy is kind of moderate, you can make a profit of $10,000. But if it goes into recession, you could lose $50,000. Do you invest or not? Well, there's more to the story, right? Each one of these scenarios has a different weight. And so they're saying, you get in touch with an economist who says, well, there's a 20% chance that the economy will be strong, 70% probability it's going to be a moderate growth, and a 10% chance that it's going to go into recession. What's your expected profit? Now then, this is just a random variable. We're going to let X profit. That means the average, the expected value, and sometimes you'll see that abbreviated like this, E of X. That's the same as the mean of X. This mean of X is what? Well, 50,000. What's its probability? What's the likelihood that the economy is going to remain strong? Okay, so 0.2, 20%. And then 10,000, these are all good numbers, times what? 70% chance. Plus, so I need a negative here. Negative 50,000 times what? That. Are those the only things that could happen? Yeah. Multiply those together and let's see what we get. It looks good on paper. What if you put your money in and instead of $12,000, you lose $50,000? Could that happen? Yeah. If we did this over and over, or if we had thousands of people investing in whatever this is, 10% of them are going to lose $50,000. But on average, we could expect to make $12,000. Is there any way to make exactly $12,000? No, it's just an average. But it's a weighted average. This is how businesses make decisions. It's a lot more complicated, but it's the same idea. So again, that $12,000 is the mean of our random variable. It's also the expected value of that random variable.